Welcome to the lecture on transient response analysis of second order system. So in this lecture we will discuss about the step response of underdamped second order system. So we discussed that a second order system in the transfer function, we saw that the highest power of s is 2 in the denominator of a transfer function, and we defined the transfer function of second order system in terms of damping ratio and natural frequency, and based on different limits of damping ratio we divided the second order system in 4 parts, that is overdamped, underdamped, undamped and critically damped system. So here we discuss more about underdamped system, because underdamped system has damping between 0 and 1, and they are the most useful system, and the damping of the systems is found between this range, that is 0 to 1. So this underdamped system we will have this GAS equal to omega n square upon s square plus 2 zeta omega n s plus omega n square, and here 0 is less than zeta less than 1. So this is underdamped system. So now the objective of this lecture is to find the transient response of underdamped second order system in the step input condition and relate this response with the parameters of the system and the location of poles. So if the system is subjected to step input, and this is output, so we have Cs equal to 1 by s into Gs. Gs is omega n square upon s square plus 2 zeta omega n s plus omega n square. Now we can write this as k1 upon s plus, so here we have second order in this denominator, so we have to take it k2s plus k3 upon s square plus 2 zeta omega n s plus omega n square. So now we can solve it. So here k1 s square plus 2 zeta omega n s plus omega n square plus k2 s square plus k3 s upon s square plus 2 zeta omega n s plus omega n square. So we can write here, we collect the terms of coefficient of s square. So s square we have k1 plus k2, then we collect the s coefficients. So here we have k1 into 2 zeta omega n plus k3 now we have k1 into omega n square, and denominator is s square plus 2 zeta omega n s plus omega n square. Now we compare this term with this numerator, coefficients of s square, s and constants. So the coefficient of s square is 0, coefficient of s is 0, and there is constant term omega n square. So, here k1 plus k2 equal to 0 and k1 into 2 zeta omega n plus k3 equal to 0, and here k1 omega n square equal to omega n square. So, from here we get that k1 equal to 1, and from here we get that k1 equal to k2 equal to minus k1, that is equal to minus 1. Now, we put these values k1 in this equation. So, we get k3 equal to, so k1 equal to 1, we put k3 equal to minus 2 zeta omega n. So, we can write Cs equal to 1 by s plus, so k2, kt is minus 1, so minus s plus k3, k3 is minus 2 zeta omega n upon s square plus 2 zeta omega n s plus omega n square. So, we can write here 1 by s minus here s plus zeta omega n plus zeta omega n, because here we take minus out and this is s plus 2 zeta omega n. We can write like this. This we can write s plus zeta omega n whole square minus plus omega n square 1 minus zeta square. Here s square plus zeta omega n is whole square plus 2 zeta omega n s, and this is omega n square. So, minus omega n square zeta square. So, this will be cancelled out. Now, we can rewrite this expression as 1 by s minus s plus zeta omega n upon s plus zeta omega n whole square plus omega n square 1 minus zeta square. So, we can write here minus zeta omega n upon, so here root 1 minus zeta square. So, we multiply and we divide. So, here upon root 1 minus zeta square upon s plus zeta omega n whole square plus omega n square 1 minus zeta square. Now, we can take these together. So, this is omega n by root, no, we can take this together, omega n into root 1 minus zeta square, that is square of that is its square is equal to this term. So, if we say a equal to omega n root 1 minus zeta square, so we can say this is a square and this is s plus zeta omega n whole square. So, this formula we know that if we take the inverse Laplace transform, So, we can write Ct equal to, so 1 by s we have 1 because this is unity function, minus this is this term, this is s upon s square plus a square. Here a is this, s upon s square plus a square is inverse, its inverse Laplace is cos at, and there is with s there is minus g, s minus minus zeta omega n. So, it will bring another term, that is e power minus bt. So, if we say b equal to minus zeta omega n, so it will be cos a into t into e power b t. So, this will be the, so 1 minus e power minus b, e power minus, so b is minus zeta omega n, so minus zeta omega n t into cos a t. A is omega n root 1 minus zeta square t. So, this is this part, because Laplace transform of cos a t equal to s upon s square plus a square, and if we say s minus b, so it will be multiplied with e power bt. Now, Laplace transform of sin a t equal to a upon s square plus a square. So, here a is this omega n root 1 minus zeta square, and we have this term minus zeta upon root 1 minus zeta square into e power bt. So, minus zeta omega n t into sin a t. So, sin omega n root 1 minus zeta square t. So, this is the response of this system. Moreover, so we can write this as 1 minus e power minus zeta omega n t cos omega n root 1 minus zeta square t minus phi. So, we can write this cos omega t plus a cos omega t plus b sin omega t as just one harmonic cos or sin with some phase difference. And here will be so 1 minus 1 upon root 1 minus zeta square. Here phi is equal to tan inverse zeta upon root 1 minus zeta square. So, here we have a cos theta plus b sin theta, and we have written it in this form cos theta minus phi, and phi is tan inverse zeta upon root 1 minus zeta square. So, here we have the response of this system. So, we can see that this in the response there is coming damping and natural frequency of this system. So, damping and natural frequency, they decides the response of the system, especially the transient response of the system. So, we can see here a typical response of a second order system, and we see here C final is the step input, and the response is rising and it is going to overshoot this final value, and then it is coming down and then trying to follow the input or final value. So, here we can see that there are the maximum peak, this is called peak, and this is maximum value of the response. Then there is the overshoot value, that how much this maximum response rises with respect to the final value. So, here from seeing the response, so we plot the, if we plot the response of this system of underdamped second order system, we can see that if this is our C final or final value, the response will rise, it will overshoot, and then it will come back down, and then it will. So, this value is called C max or peak value, and the time at which this peak value occurs is called the peak time. Then this value C max, how much it rises with respect to this, is called overshoot. Then here again this 0.1 of the final value C final is to 0.9 of this C final. This is rise time TR, and then 0.98%, that is settling time, when the response reaches to 2% and stay within that limit of the final value. So, here peak time is time required for the response to reach the first or maximum peak. Here is the peak time, the time when this first or peak or maximum occurs, that is peak time. So, let us find the peak time. What will be the peak time? So, let us collect these expressions so that we will use them to derive this time, the response characteristics, peak time and other time. So, Ct equal to 1 minus e power minus zeta omega nt cos omega n root 1 minus zeta square t minus zeta upon root 1 minus zeta square e power minus zeta omega nt sin root 1 minus zeta square into omega n t, and this is equal to 1 minus 1 by root 1 minus zeta square e power minus zeta omega n t cos omega n root 1 minus zeta square t minus phi, and where phi is tan inverse zeta upon root 1 minus zeta square. So, this is the expression, and we will use this. So, if we, let us say this is equation number 1 and this is equation number 2. So, if we want to know the peak time of this response, because this is response and it is represented by this curve. And if we want to get the peak time, we must know that peak time is the time when the response is maximum, the first maximum occurs. So if we take the first derivative of this response and equate to 0, that will give the idea of peak time. So means dct by dt equal to 0. So let's take the first derivative of this. So here 0 minus, let's take here 1 by root 1 minus zeta square, here e power minus zeta omega n t into, let's take this function, so derivative of this function first. So this is omega n root 1 minus zeta square into, and this is minus sine omega n root 1 minus zeta square t minus phi plus cos omega n root 1 minus zeta square t minus phi here, this is this minus zeta omega n into e power minus zeta omega n t. So now we can write it equal to e power minus zeta omega n t into omega n by 1 minus zeta square. So here minus we can take out, as well as this omega n we can take out. So what we will remain is root 1 minus zeta square into sine omega n root 1 minus zeta square t minus phi plus zeta cos omega n root 1 minus zeta square t minus phi. So here a cos theta plus b sin theta, let's say equal to c sin theta plus alpha, and so we can write equal to c sin theta cos alpha plus cos theta sin alpha, and so we can write c sin alpha into cos theta plus c cos alpha into sin theta. So it means we want to express this term just with a replace with single term. So we can get c equal to, we can get c so here we are getting that a equal to c sin alpha and b equal to c cos alpha. So c equal to root a square plus b square, because here a square plus b square equal to c square, and tan alpha equal to a upon b. So we can get a upon b equal to tan alpha. So here we see a equal to zeta. In this case, if we compare this, a equal to zeta and b equal to root 1 minus zeta square. So we will get alpha equal to tan inverse zeta upon root 1 minus zeta square, and C equal to a square plus b square. So a square is zeta square under root zeta square plus b square, that is 1 minus zeta square, so equal to 1. So C is equal to 1. So we can write this dct by dt equal to omega n e power minus zeta omega nt upon root 1 minus zeta square, and here 1 into sine omega n root 1 minus zeta square t minus 5, and we know that phi is tan inverse zeta by root 1 minus zeta square, and so this is equal to phi is alpha. Phi is tan inverse zeta by root 1 minus zeta square, and alpha is also tan inverse zeta by 1 minus zeta square. So here minus phi minus here plus alpha here. So this will cancel out. So we will get only sine omega n root 1 minus zeta square t. So we are getting here omega n e power minus zeta omega n t upon root 1 minus zeta square into sine omega n root 1 minus zeta square t. So now to get the maximum, so we have to make dct by dt equal to 0 to get the maxima, and to make it 0 we will have, of course this is exponential, so this can't be 0. So we have to make this sine omega n root 1 minus zeta square t equal to 0. And so omega n root 1 minus zeta square t equal to n pi, and therefore t equal to n pi upon omega n root 1 minus zeta square. Now for n equal to 0, for n equal to 1 we will get the first maxima, and therefore that t equal to Tp, and that is equal to pi upon omega n root 1 minus zeta square, and this we can also write pi upon omega d. So here peak time is equal to pi upon omega d. Omega d is called the damped frequency, and this is equal to omega n root 1 minus zeta square. So here we can see that from the step response of the underdamped system, second order system, we found the response of the system, and then we find the peak time by taking the first derivative of that response with respect to time equal to 0, and we get this peak time. So this is the Tp is the peak time when this maxima, first maxima occur, and that is equal to pi upon omega d. So we will continue other parameters in the next lecture. So I thank you for attending this lecture, and see you in the next lecture. Thank you.